In the beginning, there was nothing. And then, bang, AEL was born. Astro's Electronics Lab brings you entertaining, sometimes silly videos relating to electronics for your enjoyment. Follow along with his frustrations and antics and maybe learn something in the process.
Greetings, the Astro 30 here, yet again, with another short electronics fundamentals video for you. Today we're going to look at a very popular circuit that's been around ever since I'm going to say, since valves were invented, or tubes, is the Astable multivibrator circuit. Now, I'm not sure if that's the correct way to pronounce multivibrator, but that's how I'm going to pronounce it, but I think from now on we'll just call it a flip-flop. And that's basically what it is. This is known as a relaxation oscillator, and it's a self-starting, self-oscillating circuit. And with the capacitor resistor values here and here between the bases and the collectors, we get roughly a flash rate on this LED over here of about 1 Hertz. That's 500 milliseconds on, 500 milliseconds off, within a few hundred milliseconds error. Now, to explain the operation of this circuit is fairly involved. So I'm going to switch to a computer graphic and actually read a prepared statement of how the circuit actually works. I think that'll be a lot easier. The Astable multivibrator, or flip-flop, consists of 2 cross-coupled resistive capacitive amplifiers. The circuit has 2 unstable states. When VC1 is low and VC2 is high, then Q1 is on and Q2 is off. When VC1 is high and VC2 is low, then Q1 is off and Q2 is on. When the circuit is first powered up, then neither of these transistors are turned on. The base voltage of both transistors starts increasing. Any one of the transistors can turn on faster due to the difference in doping and electrical characteristics of the transistor. We cannot say which transistor is going to conduct first, so we assume that Q1 conducts first and Q2 is off, C2 being fully charged. Q1 conducts and Q2 is off, hence VC1 equals 0 volts since all the current is bypassed to ground due to short circuit of Q1. And VC2 equals VCC since all the voltage drops at VC2 due to it being an open circuit. Due to the voltage of VC2 being at VCC, C2 starts charging via Q1 through R4 and C1 starts charging through R2 via Q1. The time taken to charge C1 is greater than the time it takes to charge C2. As C1's right plate is connected to the base of Q2 and is charging, so this plate is at a higher potential, and when it exceeds 0.65 of a volt, then it turns on Q2. As C2 is now fully charged, so its left plate is at minus VCC, or in this case minus 5 volt, and is connected to the base of Q1, hence it turns Q2 off. Now Q1 is off and Q2 conducts, therefore VC1 is equal to 5 volts and VC2 is equal to 0 volts. C1's left plate is previously at a voltage of minus 0.65 volt, which starts rising to 5 volt and is connected to the collector of Q1. C1 first discharges from 0 volt to 0.65 volt and then starts charging through R1 via Q2. During charging, the right plate of C1 is at a lower potential which turns off Q2. C2's right plate is connected to the collector of Q2 and is previously at plus 5 volt. So C2 then discharges from 5 volt to 0 volt and then starts charging through R3. The left plate of C2 during charging is at a higher potential which turns on Q1 when it reaches to a voltage of roughly 0.65 of a volt. Now Q1 conducts and Q2 is turned off. The above sequence repeats and we get a waveform at both collectors of the transistors which is out of phase with each other. So with the circuit explained as best as I can, and I hope you understood it because the workings of it is fairly complex, and on first glance the way you look at it, it shouldn't work at all, but it does. Anyway, let's move on to a breadboard version of that exact circuit and see how it operates. Alright, so I have the multivibrator circuit built up on the breadboard. I'm still not really sure how you're supposed to pronounce that word, so we'll call it a flip-flop from now on. But I've got one blue LED on the second transistor's collector via a 10k resistor, and I've got the power supply hooked up across where it needs to go, and it's going to be set at 12 volts, or pretty close to it. On channel A there I've got it at 11.5, so I'll just turn the load on, and immediately it starts oscillating. And my estimation was correct, it's around about 1 Hertz or 1 cycle per second. So the LED's on for 500 milliseconds and off for 500 milliseconds. Plus minus 100 milliseconds. Isn't that special? So what I'm going to do now is I'm going to hook up the oscilloscope between ground and the collector of the first transistor, and we're just going to scope what it looks like on the screen. Alright, so we need to connect between ground and the collector of this transistor, which is that resistor there. And as we look at the scope trace there, and I'm on a fairly high time base, we can see the actual capacitors charging and discharging, plus the transistor's collector slamming to negative on that cycle, which is kind of interesting. So that's what the oscillator circuit looks like on an oscilloscope screen. Now there's one other thing we can actually do with this. If we were to say bring the base of this transistor to ground, like have a switched input, then we can make this LED permanently stay on, because then the oscillation stops. And what is the purpose of this? Well, you could use it as a dual indicator board, so it flashes to give you like an error warning, and then when there is no error, I'll just remove this scope lead. That's what this extra wire hanging out in the breeze is for. If it was suddenly brought to ground on that first transistor's base, the LED stays permanently on. So you could use this as a form of power indication, fault indication, such as in an amplifier's DC protector circuit. One other thing to note is the higher that input voltage is to the circuit, the faster it's going to flash and the brighter the LED is going to be. And conversely, the lower the voltage, the slower it's going to flash and the duller the LED is going to be. So to demonstrate that, I will start winding the voltage up to around about 15. I don't want to go too far. As I wind the voltage up, the flash rate is starting to change. So it's getting a little bit faster now, and the LED is getting brighter and brighter. And I'm now at roughly 15 volt, and it's a lot brighter. Conversely now, if I start reducing the voltage, now we're at where we were, 11.5, keep going down, we're at 9 volt now, it's starting to get a little bit slower, 8 volt, oops, we dropped right down to 7.3, and as we can see, it is having a little bit more trouble maintaining oscillation. At 5 volts, it's getting a little bit duller. The flash rate's not changing that much. If I go right down to 3 volts, say, its flash rate has increased a little, but it's hardly turning on at all. And we're at about 2.7 volts. So the circuit is now starting to fall out of oscillation. And at 2.3 volts, it's completely dead. So the resistor values in this circuit are very, very important for the voltage that you're putting into it. So I'll wind that back up to 11.5. About there. And that's where we started. Isn't that neat? So there you go. There's the Astable Multivibrator circuit. Very, very interesting. Anyway, I hope you found this video interesting. If you did, please go down below, like, comment and subscribe, and even share the video on social media. That'll help me out a great deal. And as always, thank you for watching. This is the Astro 30 saying see ya. Have a great day.